Last day we looked at the same gas at different temperatures. Today we are looking at different gases at the same temperature. So we have helium, neon, argon, krypton, and xenon. So we could actually label those so it looks a little easier for us to. This one here is helium, neon, argon, krypton, and xenon. So, what are our questions on this? Let's find out. List the noble gases that are represented in the graph in Model 2 with their average atomic masses. Can you do that? Beta, are you here for? Okay, yes. No? Okay. Hi. The quiz. Yeah. So you guys are writing that while I'm getting this quiz, okay? Quiz. Helium 4.0, argon. Yeah, 20.2. Helium, neon, argon, krypton, xenon. Huh? You guys are good? Okay. 39.9, 83.0, and xenon 131.3. All right. Which variable explains the difference in the distribution curves for the different noble gases in Model 2, temperature or mass? Yeah. Mass. I'm not going to have you explain your reasoning. I mean, it's pretty obvious. They're all at the same temperature. Which noble gas has the slowest average particle speed? Who has the slowest? Xenon. Slowest. Who has the fastest? Helium. In a complete sentence, describe the relationship between the molar mass of the particles and the average speed at a given temperature. Can you guys do that? So, as the molar mass of the particles increases, the average particle speed at a given temperature decreases. Does that make sense to you? Does it make sense that if we give them all the same energy, the bigger ones the heavier ones are going to move more slowly? Yeah, because if you push something, right, and it's small, it's going to go farther than if you push something else with the same energy and it's bigger. Consider the distribution curve for fluorine. Sketch an approximate distribution curve for chlorine gas at 100 degrees on the same graph. So you have to think what's going to happen to the height of the peak, what's going to happen to the location of the peak, what's going to happen to the right-hand edge. Should the peak be higher, lower, or the same? Higher. Should the peak be moved to the left, to the right, or stay the same?
Right.
So it's going to be higher and to the right? Like that?
Right.
Left? Your other right, right? Your other left? Okay, yeah, absolutely. Okay, so here we go. And what should happen with our tail? Should our tail off to the left of this one, to the right of this one, or in the same place? So should it end here, or here, or here? A, B, C. A. Yeah. And it shouldn't actually touch the line. It's really hard to draw though, so. So it should not actually touch the y-axis. Excellent. X-axis. Thank you. There we go. That's better.
None of them touch the x-axis.
None of them will touch the x-axis. They might look like it, but they really shouldn't. The x-axis is an asymptote. Is good? Cool. All right, model 3, kinetic energies. Here we have helium at different temperatures. And then we have kinetic energy of noble gas molecules at 100 degrees. All right, what is the variable and unit of the x-axis for both graphs? This is easy, just read it. It is kinetic energy. In joules. What variable, temperature or molar mass, is being varied in the graph on the left? Temperature. And that would mean that on the graph on the right, just in the inbox there is great. No, we started on the lab yesterday. You can pick it up just on the side there. There's 2 big long pieces of paper. On the side, by the blue thing. Yeah, got it. Okay. Which variable, temperature or molar mass, is being varied on the graph on the right? That would be our molar mass. Does that graph look okay to you? No. Okay, maybe it's not supposed to. Let's find out. Describe the relationship between the average kinetic energy of the particles in a sample and the temperature when molar mass is held constant. As average kinetic energy increases, what happens? What? Oh, as temperature increases, as temperature increases, average kinetic energy does what? Increases. Describe the relationship between the average kinetic energy of the particles in a sample and the molar mass. Well, this irritates me. Why are they all in the same place? What should it look like? We got helium. Helium should look like this. Yes, hi. Is this, which one is this? Re-quiz for the last one?
Yes.
Okay. Oh, that's A. B. B, B, B. No, that's not it. Okay. Huh. 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 Oh. Oh. Kinetic energy, not speed. Ah. It is correct. My apologies. Okay. Average kinetic energy of the particles and the molar mass. Okay. As molar mass increases, hi. No. As molar mass increases, kinetic energy stays the same. Compare and contrast the graph on the left in Model 3 with the graph in Model 1. Okay. I'm going to grab this graph here. Whoops. And put it beside Model 1. The graph on the left. Thank you. Oh, for God's sake. Stop doing that. Okay. Sorry. There we go. Now I should be able to put it beside it. Maybe. No. So sorry. I don't know what's wrong with it. Okay. There we go. Well, in both of them, the average temperature, or sorry, the average speed increases, yes? And the average kinetic energy increases. Okay. And now, we're not going to write it down. We're just going to let that be for a moment. Okay, and we're going to grab this one. There we go. And we're going to put it beside this one here. That's different, isn't it? What is temperature?
Average kinetic energy of
Temperature is the average kinetic energy of the particles. Okay. So if they're all at the same temperature, they all have the same average kinetic energy, but they won't all have the same speed because their masses are different. Okay? So basically, we can say that at the same temperature, this is what? 24. Yeah. At the same temperature, all the noble gases have the same kinetic energy, average kinetic energy, because temp is a measure of average kinetic energy. So it makes sense that if the temperature is the same, the average kinetic energy is the same because they're the same thing, essentially. Temperature is just one way of measuring it. At the same temperature, though, the heavier molecules move slower and the lighter molecules move faster. Okay. And this is all because of this particular little formula here. Kinetic energy is equal to 1/2 mv squared. So kinetic energy increases, like if you increase the if the kinetic energy is the same, if the mass increases, the velocity must decrease. Use the equation above to explain the variation in the distribution curves in the graph on the left in model 3. So we are looking at different temperatures. I don't know. This one makes me unhappy, and I don't think you're ever going to have to answer it. Explain how the variation in the distribution curves in the graph in the left in model 3. So that would be this one. At a higher kinetic energy, the velocity would have to be, at a higher kinetic, what am I trying to say? At a higher temperature, the particles move faster, yes? So what that means is that v, velocity, has increased. Yes, the speed has increased. And if V increases and mass stays the same, then kinetic energy equals 1/2 mv squared, it will increase. You are not going to have to explain this on the AP exam. But if it helps you to understand what's going on in the curves, that's a good thing. Huh? What do you mean a spike? Why is it tall? Oh, just because it's a lot narrower. So in order to have the same area under the curve, if something is taller, the area under the curve represents the total number of particles. Let's write that down. Area under curve equals total number of molecules. So this has to do with integral calculus, right? How you find the area under a curve. Basically what you do when you're finding the area under a curve is you pretend you've got a histogram. Okay, I've drawn a terrible histogram. But what you do is you keep making your slices smaller and smaller and smaller and smaller and smaller and smaller and smaller. And then you add up all the heights, and then that'll give you the total number of molecules. So if you say, how many molecules do I have at 10,000? Well, I've got 25 molecules. How many do I have at 10,001? Well, I've got 20 molecules. And then you have to add them all up. And that's what calculus lets you do. That's the math tool you would use to add up all those infinite tiny slices. But you don't need to know how to do that. You just need to say the area under the curve is the total number of molecules. Is good? You're going to ask me later. You can come and ask me because I got to let the grade 8s in here for their class.